Next we will discuss the quantum theory of anomalous Zeeman effect. Like we will explain anomalous Zeeman effect by using quantum theory. What is anomalous Zeeman effect? Anomalous Zeeman effect is the splitting of spectral line into a number of component lines, more than 3, in the presence of a weak magnetic field is known as anomalous Zeeman effect. Anomalous Zeeman effect can be explained by using the concept of spin of the electron. Now, according to vector atom model, the total angular momentum J will be equal to the sum of orbital angular momentum and spin angular momentum, where L, magnitude of orbital angular momentum, is L into L plus 1 square root h bar. Magnitude of spin angular momentum is S into S plus 1 square root h bar. And magnitude of total angular momentum is J into J plus 1 square root h bar, where L is the orbital quantum number and L values started from 0, 1, 2 and so on. S is the spin quantum number and its value is either plus or minus 1/2. And J is the total quantum number and its values is from L plus minus S. Now, we already derived the relation for the magnetic moment due to orbital motion is magnetic moment due to orbital motion is mu L, which is equal to E h bar over 2m into L. Let's say this is equation 1. And similarly, the magnetic moment due to spin, magnetic moment due to spin is mu s, which is 2 times E h bar over 2m into L. And similarly, the total magnetic moment, this is equation 2, total magnetic moment due to total angular momentum J is total angular momentum, total magnetic moment of the atom will be, which I represent by this mu J, which will be equal to the vector sum of magnetic moment due to orbital motion plus magnetic moment due to spin motion. And the magnitude of mu J of total magnetic moment mu J is equal to E h bar over 2m, and we have J into G, where J has values which is 1 plus J square plus H square minus L square over 2J square. Let's say this is equation 3, then this will be equation number 4. Also, we know that EH over 4 pi m, a Bohr magneton mu B is equal to EH over 4 pi m, This is Bohr magneton. So it means that this equation 3, which can be written as mu j, which is EH bar. So we have EH over 4 pi m, because H bar is H over 2 pi. EH bar over 4 pi m, and we have J into G. So we replace this EH bar over 4 pi m by this Bohr magneton. So the total magnetic moment will be mu b J into G. This is equation number 5. Now when a magnetic dipole is placed in a uniform magnetic field, when magnetic dipole is placed in a uniform magnetic field B, potential energy acquired by dipole, potential energy acquired by the dipole is, which I represent by Vm, which is equal to total magnetic moment times B into cos of theta. This is equation number 6. Now using equation 5 and 6, we have the potential energy acquired by the dipole Vm, which is equal to, instead of mu j I will put this value, which is mu b jg into b cos of theta. I can write it as mu b Bohr magneton, then we have this Landis factor, G factor, then we have magnetic field, and then we have J cos of theta. What is J? J is the total angular momentum, and here we have the magnetic field B. Now the component of this magnetic J in the direction of magnetic field is Mj, which is, I call it Mj, which is equal to, this is, let's suppose, theta, which is equal to J cos of theta. So I replace this J cos of theta by this total magnetic quantum number, then we have mu b gb into mg, which is potential energy acquired by the dipole in the magnetic field. This is basically the projection, this mj is basically the projection of j in the direction of magnetic field. Now this is equation number 7. Now as we know that when an electron jump from higher energy states, higher energy I represent by E naught I, to some lower energy states, which I represent by E naught F, in the absence of magnetic field, it radiate energy in the form of photon. Its energy is h nu naught. This energy will be equal to the difference in energy of the two energy states, which is E naught I minus E naught F. So I can write h nu naught is equal to E naught I minus E naught F. This is the energy emitted by electron due to transition from higher energy states to lower energy states in the absence of magnetic field. Now, in the presence of magnetic field, what will happen? We have the atom's energy is this E naught in the absence of magnetic field. Once we apply magnetic field, then we have extra term, potential energy also stored in the atom, which is this. So the total energy will be the sum of this atomic energy plus the potential energy acquired in the presence of magnetic field. So total energy will be equal to, this is in the presence of magnetic field B. Total energy will be equal to E naught, the atom's original energy plus the energy stored due to magnetic field Va, where E naught is the energy of the atom without magnetic field and Vm is the energy stored in the atom due to magnetic field. Or we can write E naught, E is equal to E naught plus Vm value is this one, which is mu B G, and we have then B, and we have Mg. This is equation number 9. Now, in the presence of magnetic field, what will happen? We have electrons. This is when B is not equal to 0. We have electron jump from higher energy states, which I call EI, to lower energy states, which I call EF, such that EI will be equal to E naught I plus mu B, and then we have B, we have GI MJ I, and EF is E naught F plus mu B B GF MJ F, because this G has different value for this energy state and it says different value for this energy state. Similarly, Mj has different value for this energy states and different value for this energy states. That's why you put initial and final here. Once electron jumps from this higher energy states to lowest energy states, it's also radiate energy in the form of photon with energy h nu, which is equal to the difference of the two energy states, which is EI minus EF. So we have h nu, which is EI minus EF. Or we can say that h nu will be equal to, using this value and this value here, we have E naught I plus mu B B GI MJI minus E naught F minus mu B B GF MJF. So if I rearrange the term and simplify it, we get nu is equal to E naught I minus E naught F over H bar plus mu B is common here, so here we have mu B B, and then we have H bar, and here we left with H bar, not H bar, it's H. Here we left with GI MJI minus GF MJF. Now using equation, this is 7, this is 8. Yes. this is, yes, using equation 8, which is nu naught is equal to E naught I minus E naught F over H. Here we get nu is equal to nu naught plus mu B over H, and we have this GI MJI minus GF MJ. We can write nu is equal to nu naught plus delta nu into GI MJI minus GF MJF. Here we define where delta nu is equal to mu B over H, and mu B value is, this is the Bohr magneton, which is EH over 4 pi m times B over H. H cancel with this, so this is EB over 4 pi m. Now the change in wavelength, frequency of the spectral line, this change in frequency of the spectral line, which is EB over 4 pi m, this change in frequency of the spectral line is proportional to the magnetic field, strength of the magnetic field. This is the quantum theory of anomalous Zeeman effect. In the next section, I will discuss the splitting of D1 and D2 line of sodium in weak magnetic field by using the concept of this equation. We have this factor is very important, Ji Mji, or this factor or this factor. So we have these three factors. One is J, the other one is Mj, and the third one is the product of J and Mj. These are very important, which we will discuss in the next video once we explain the splitting of D1 and D2 line of the sodium in a weak magnetic field. Thank you.